So today I would like to take this opportunities to give a overall highlight of our research interests, and hopefully this can be a chance that I can find more collaborators within our Stevens community. So first, I would like to use this figure to briefly introduce the object we are starting on. So we are looking at the power system. So traditionally, we use a lot of generation stations through transmission and distribution lines to supply different types of the load. So in terms of the sustainability, so in the emerging power systems, we see a lot of new generation resource, renewable generation resources, and the cleaner devices at both the generation side and also the demand side. So we see a lot of small wind turbine and the PV panels. So within this big picture, so our group is trying to understand the challenges and see how we can make better decisions to manage this big system. So if we look at the big picture for the power system, usually we are looking at several different problems in different time dimensions. So in the longer time dimension, annually based, so we are looking at the planning problem. So where and how many renewables we want to put in different locations. And moving downward in a monthly basis, we probably will look at some of the maintenance and fuel contracts, those things. And even move forward, we are looking at the day ahead, hour ahead, and minutes ahead based schedule. So this schedule will determine, for example, which generator needed to be turned on and how many electricity in terms of the megawatts will be generated to supply the load. And the last one, usually we are looking at the second, millisecond level to do the real-time control of the system, make sure the security of the operation. So when we look at this entire time train, so we are facing with several different types of the complexity. So the first one is the temporal complexity, as we explained here. When we look at the annually based decision making all the way down to the second based, there is a wide range of the time you have time span you have to cover and how to coordinate these different decisions made at different times. A second challenge is called the spatial complexity, because we are looking at a bigger system that cross many states or even many countries. So we have transmission and distribution. So this is the spatial complexity as well. The last complexity is related to different entities in the system. So we have generators, we have consumers. So how they can coordinate, or in many times they will compete with each other to make a cheaper or make a cleaner electricity. So it's called contextual complexity. So basically our research group, we're trying to tag these different problems in different angles. So one of the good things is that from the mathematical point of view, we probably can simulate all these different problems in one form or the other. So in general, we can formulate them as some type of optimization problems like this, either linear or nonlinear. For some of the problem, we are going to solve a system of nonlinear equations to get a solution of X. And sometimes we are dealing with this differential equations. So this is a system of equations. So the steps to solve the problem will be first how we can abstract from the physical system to build our mathematical model, and then how we can effectively solve this model to get a solution and apply it to the system. So the first thing in terms of the modeling part, so we always want to build a more accurate model in order to map with the actual power system. But if you get a finer model, probably your solution time will be much longer, not acceptable. So here I give a very brief example of a typical generation plant. So this is a combined cycle unit. So basically, in one combined cycle unit, we may have several combustion turbines and steam turbines. So basically, they use the combustion turbine to convert from gas to electricity, and they can also collect the waste heat to generate further electricity in a second stage to improve the overall efficiency. But since this covers several turbines, so if we operate this entire power plant we are facing with several different operation modes. So how many combustions we are going to turn on and how many steams we are going to turn on. So this is not a single unit. Basically, it's a couple of multiple turbines to coordinate them together. So from the mathematical point of view, we may need to simulate many different operation statuses and see which one will be the best. And again, this will be a leverage in terms of the modeling accuracy and the complexity you may be facing with in a later time when you solve the problem. The second major thing we are looking at is from the algorithm point of view. So we always try to solve the models as quick as possible. So here I try to present this idea in either way. So the first attempt, usually we are going to solve the problem ahead of time. So which means that if we want to get a solution at the time t, probably we need to prepare for this solution 5 minutes or 10 minutes ahead of time. So we need to forecast some states of the system at t, and we try to use this delta t time to make the decision so that the decision can be applied to the physical system when t comes. So we call it ahead of time. So the next step is whether we can do in a better way. A better way means whether we can shorten this delta t time. So we call it near real time. So this means that if the time is shortened, we can get a better forecast value. So it's a general sense that if time is closer, probably we can increase the accuracy of the forecast. So this will give you a better solution, but this depends on how fast you can solve the problem. If you can solve it faster, basically you can get a better solution at the time t. Because of one major reason is because you can improve the forecast accuracy of the system state at time t. And the last try, we are trying to make this near real time to be even better. We call it faster than real time. So the basic idea is that if we can even solve the problem even faster, so we are not only to determine the solution at the time t, we are also going to expand the system simulation from t to a near future. So the way, a benefit of doing this is that, so when you make the decision at the time t, if you can also simulate the system dynamic behavior in the next 10, 20 minutes, you can see how good or how bad your decision is, and you can make a predictive action if the decision is bad. So that's basically means I borrowed this figure from the internet showing that if you can see into the future, basically you can adjust your decision at the t. If it's dangerous, you can revise your decision and make a better decision to get some treasures in the future. So these are some of the attempts we are trying to solve from the computational challenge. So mathematically, again, once we have these models, we are trying to make the computational time to be faster and faster. So we tried a different mathematical optimization problem. We dig into some of the parallel and cloud computing solution platforms. And we also studied some of the artificial intelligence and the machine learning based approach, try to combine all this together to achieve some of the goals in our computational performance. And the third thing we are trying to do is go back to this time chain we are looking at. So the current strategy in the power industry and probably in many other industries that they make this time-dependent decisions in a sequential way. So they do the planning, and then based on the planning decision, they do the monthly, and they do the daily, they do the second based. So one of the consequences is that this is a kind of open loop decision-making procedure. So there is no way to guarantee that in terms of the near time or day ahead solution, there is no guarantee that the solution you made before is the best at the current situation. So I borrow a very simple example to show you here, a cigarette. So we all know that the cigarette is not healthy. So people, the scientists are looking at more healthier cigarettes to improve our healthy. But the consequence, if we do this open loop the decision making, the consequence may not be what we expect. The reason is that people saying that cigarettes are becoming more healthier, they try to smoke more, and probably they get worse, even worse than before. So in order to close the loop of this system, so what we probably should do is we evaluate the different technologies or solutions, and simultaneously we evaluate how the people will react to this solutions and the technologies, make the closed loop decision, and the final technology you will find out shall be able to improve the healthy life of our people. So the same thing, when we make the long-term decision, we want to close the loop so that make the entire decision procedure to be better for not only the annual-based, but also for the day-ahead and even the second-based decision-making procedure. So these are basically the three major aspects our research team has been looking at. So the last thing I want to briefly mention here is besides the power system, we are also looking at some of the interdependency issues. So actually, power system is highly interdependent with many of other infrastructure systems. For example, the gas, the water system, the transportation, and the communications for supporting them and also rely on them for its own support. This is my last slide. I just show a bunch of tightening relationship between the power system in red and the natural gas system in blue. We see a lot of these coupling elements that highly tie the two systems. So that urges us to look at some of the interdependent models and the solution approach to make this to be more sustainable and more reliable for our society. So I think that's all I have. And thanks again for the opportunity. Yeah, Henry, you're muted.
Okay, all right, thanks very much, Lei. There is a question in the Q&A box. For some reason, I cannot open it.
Yeah, I can.
Open it and read out loud what the question is.
Okay, the question is, are generating transmission facilities currently capable of reacting in real time to demand fluctuation? The answer is yes. So currently, most of the time, the generation resources will react to demand fluctuations in real time in millisecond-based even. So there are some real-time controllers that can do it. But with the renewable generations, we need to make sure that this is still the case because the fluctuation will become more significant than nowadays.
Great, and also there's another question, maybe the last question. Would you mind?
Yeah, the last one is, has your research considered the cybersecurity concerns within the interdependent systems? Yeah, the answer, yeah, we are currently, I currently working with several faculties within our department. So one of the projects we are looking at is, IoT-based cyber attacks, how that will impact the security of the smart grid or power systems.